Welcome to the class. Till time we have seen that how ideal Brayton cycle is, how to estimate the state variables, and what is the particular expression for calculating different interactions like work and heat interaction in different processes. Now let us execute it through solving some examples on ideal Brayton cycle. So here is the first example. It states that a gas turbine works between 300 Kelvin and 900 Kelvin temperature while pressures are 1 bar and 4 bar. Find out efficiency net work in kilowatt if mass flow rate is 1600 kg per minute. Let us plot our TS diagram for the Brayton cycle. So this is T and this is S. We know that processes 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So given thing over here is T1 is equal to T min. It is given as 300 Kelvin. T3 is equal to T max is given as 900 Kelvin. Further, we are told that P1 is equal to 1 bar, but it is also equal to P4. It is also told that P3 is equal to P2 is equal to 4 bar. And we are supposed to find out efficiency, and W net m dot is given as 1600 kg per minute. So we need to find out efficiency. For that, first let us find out Rp. Rp is equal to P2 by P1, which is equal to 4. So now pressure ratio is known to us, but this 4 is also equal to P3 by P4. We know that efficiency of Brayton cycle is 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. Here for that we know that we are working with air as a gas with gamma 1.4, and this leads to gamma minus 1 upon gamma is equal to 0.285. So having said this, efficiency is equal to 1 minus 1 upon 4 raised to 0.285 is equal to 0.3263, or efficiency is equal to 32.65%. We are supposed to find out now network. So for network we know that W net is equal to m dot into H3 minus H4 minus m dot into H2 minus H1. Basically this is Wt minus this is Wc. So net work is turbine work minus compressor work. While deriving the expressions, we were considering specific work, so we had unit of kilojoule per kg. But now we have to multiply by mass flow rate, and it's a steady flow process, and there is only one mass flow rate through the complete circuit. So mass flow rate in the compressor is same as the mass flow rate in the combustor, which is same in turbine and pre-cooler. So mass flow rate is same, but mass flow rate it is given to us as 1600 kg per minute. So this is equal to 1600 divided by 60 in kg per second. So m dot is equal to 26.67 kg per second. So W net is equal to m dot, and then we can take Cp common from everywhere, so it is T3 minus T4 minus T2 plus T1. Here the known things are T3 is known, T1 is known, but we don't know T2 and T4. So let us evaluate T2. T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma, and then this turns out to be 445.35 Kelvin. Then T4 is equal to T3 divided by Rp bracket raised to gamma minus 1 upon gamma, and it turns out to be 606.26 Kelvin. So let us put all these numbers and try to evaluate. 26.67 into Cp is 1.005 into 10 to the power 3 joule per kg Kelvin, but it is asked to us to find in kilowatt, so we will put kilojoule. So it is 1.005 kilojoule per kg Kelvin, and then T3 is 900 minus T4 is 606.26 minus T2 is 445.35 and T1 is 300. So after multiplication we will get W net is equal to 39.77 into 10 to the power 3 kilowatt. So this is other answer of the example. So this is how we will execute the known expressions to solve an example. So let us go to the next example. It states that an engine operating on Brayton cycle has pressure ratio of 8. Air enters the compressor at 0 degree Celsius and 100 kPa pressure. Maximum cycle temperature is 1500 Kelvin. Among two turbines, high pressure turbine develops power enough to run the compressor. Determine the exit pressure and temperature of high pressure turbine and mass flow rate if the work output is 200 megawatt. Now this example says that there is a compressor which gets air at station 1, and then air goes to the combustion chamber. From the combustion chamber it goes to the turbine, and then these two are connected to each other. So this is high pressure turbine, and from that air goes to the low pressure turbine, and then it goes as an exhaust low pressure turbine. So 1 to 2 is compression process, 2 to 3 is heat addition, 3 to 4 is high pressure turbine, and 4 to 5 is the low pressure turbine. So we have TS diagram for this example as similar 1 to 2, 2 to 3, but we have intermediate point 4 and then 5. So let us evaluate for the known things here. Given things are, we are told that P1 is equal to 100 kPa, T1 is 0 degree Celsius, which is 273 Kelvin. We are told that Rp pressure ratio is 8. Further, maximum temperature of the cycle, which is T3, which is T max is 1500 Kelvin. We are supposed to find out the network, we are supposed to find out mass flow rate if W net is equal to 200 megawatt. We are also supposed to find out P4 and T4. So let us evaluate. Before that, we'll need to find out one number which is always encountered in this example. So we'll isolatedly find out Rp raised to gamma minus 1 upon gamma. So it is 8 raised to 0.8285, and it turns out to be 1.808. So let's find out T2 first. So T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma. We know T1, it is 273 into 1.808. So it gives us T2 as 493.58 Kelvin. We are told that work done in high pressure turbine is equal to the work input to the compressor. We know that work done into the high pressure turbine is H3 minus H4, and work input to the compressor is H2 minus H1. So we can take specific work here since m dot would get cancelled. So in this perspective, we can say H4 is equal to H3 minus H2 plus H1. So T4 Cp would get cancelled, T3 minus T2 plus T1, and we know T3, and T3 is given as 1500. T2 we have evaluated 493.58, and T1 we know it is given 273. So T4 is equal to 1279 Kelvin. So knowing this, we can find out the pressure at the exit of the high pressure turbine, and we know that P3 by P4 is equal to T3 by T4 bracket raised to gamma upon gamma minus 1. This is a different index. If it would have been pressure, then it is pressure ratio raised to gamma minus 1 upon gamma, but for temperature ratio it is gamma upon gamma minus 1. So T3 is known to us, it is 1500, and T4 is 1279 bracket raised to 1.4 bracket divided by 0.4. So this turns out to be 1.74. So we know that now P3 is P4 is equal to P3 divided by 1.74, but P3 is equal to P2, so it is P2 divided by 1.74, but P2 is equal to P1 into Rp divided by 1.74. So P4 is equal to P1, and P1 is 100 kPa into 10 to the power 3 Pascal. Rp is 8 divided by 1.74. It gives us pressure P4 as 459.7 kPa, or into 10 to the power 5 Pascal. Now we can find out mass flow rate, since W net is only W of low pressure turbine. Since high pressure turbine exclusively runs the compressor. So WNet is only low pressure turbine work. So WNet is given as 200 into 10 to the power 6 is equal to m dot into H4 minus H5, but here we should know T5. So for that, further we can write W naught is equal to 200 into 10 to the power 6 is equal to m dot Cp T4 minus T5, and let us evaluate T5, where T5 my T4 is equal to P5 by P4 bracket raised to gamma minus 1 upon gamma. So then it can also be evaluated from the formula T5 by T3 is equal to P5 by P3 bracket raised to gamma minus 1 upon gamma. Since P5 upon P3 is equal to 1 upon Rp, so T5 is equal to T3 divided by Rp raised to gamma minus 1 upon gamma, and it turns out to be 829.6 Kelvin. Putting this T4 in this expression of WNet, we can get 200 into 10 to the power 6 is equal to m dot into 1.005 into 10 to the power 3 into T4 is known to us 1279 minus 829.6. So this gives us m dot is equal to 442.82 kg per second. So this is other answer of the example. So we evaluated pressure, temperature at the exit of the turbine, and we also found out what is the mass flow rate in the circuit. So this is how we could solve the example. Let us move to the next example. Next example states that an aircraft engine operates on pressure ratio 10. Heat is added to the cycle at the rate of 500 kilowatt. Mass flow rate of air is 1 kg per second. Conditions at the inlet are 70 kPa and 0 degrees Celsius, and we are supposed to find out power and efficiency of the cycle. So let us plot the TS diagram such that we can remember the states for which we are giving the numbers. So given things to us are, we are told that Rp is equal to 10, Q in is equal to 500 kilowatt, which is equal to 500 into the 10 to the power 3 watt. M dot is equal to 1 kg per second. We are told that P1 is equal to 70 kPa and T1 is equal to 0 degree Celsius, so it is 273 Kelvin. So let us first, as required, we will find out a most required number, which is Rp raised to gamma minus 1 upon gamma. So Rp is 10, gamma minus 1 upon gamma is 0.285, so it turns out to be 1.92. Then we can find out T2 hereafter, which is T1 into Rp raised to gamma minus 1 upon gamma. So it is 273 into 1.92, and this number turns out to be 524.16 Kelvin. We can find out T3, but for that we can use m dot into H3 minus H4 is equal to Q in. So m dot is 1 kg per second into Cp is 1.005 into 10 to the power 3 joule per kg Kelvin into T3 minus T4 is equal to T3 minus T2 is equal to 500 into 10 to the power 3. So 10 to the power 3 gets cancelled. So we get T3 is equal to 500 divided by 1 into 1.005 plus T2, and T2 is 524.16. So for us T3 turns out to be 1021.67 Kelvin. Then we can find out T4. As we know, T4 is equal to T3 upon Rp raised to gamma minus 1 upon gamma, where T3 is known to us now as 1021.67 divided by 1.92, and this number turns out to be 530.04 Kelvin. Now, knowing all these temperatures at all the corners, we can find out W net, and which is equal to m dot Wt minus Wc, and Wt is m dot into Cp into T3 minus T4 minus m dot Cp into T2 minus T1, that is turbine work, compressor work. So m dot is known to us, it is 1 kg per second, and Cp is 1.005 into 10 to the power 3. This is equal to T3 minus T4 minus T2 plus T1. So W net is equal to 1005 into T3 is 1021.67 minus T4 is 530.04 minus T2 it is 525.16 plus T1 it is 273, and this gives us net work as 241.67 kilowatt. So we can find out efficiency as W net upon Q in, where Q in is given to us. So looking at this, efficiency becomes 483, so it is 48.3%. So this is the efficiency of the Brayton cycle. Move on to the next example. We have been given as work ratio of a gas turbine plant is 0.563, its thermal efficiency is 0.35, inlet temperature to the compressor is 300 Kelvin, and mass flow rate is 10 kg per second. We are supposed to find out temperature drop across the turbine. So again let us plot the TS diagram and let us see what are the given things for this cycle. It is given to us that work ratio is 0.563. So we are told that W net upon Wt is 0.563. We are told that efficiency is 0.35. it is also told that T1 is equal to 300 Kelvin and m dot is equal to 10 kg per second. We are supposed to find out what is T3 minus T4, or which is delta T turbine. So let us see, we can use directly the formula for efficiency, 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, and that is equal to 0.35. Using this we can find out Rp, and Rp turns out to be 4.533. So pressure ratio is known to us. We know that Rw is equal to work ratio, and then the formula for work ratio of ours was Rp raised to gamma minus 1 upon gamma divided by beta, and then this beta was T1, 1 upon beta is T1 upon T3, so it is Rp raised to gamma minus 1 upon gamma into T1 by T3 has minus sign, it is which is getting subtracted from 1. So here Rw is given to us as 0.563. So T1 is known to us, so 1 minus 300 divided by T3 into Rp raised to means 4.533 bracket raised to 0.285 is equal to 0.563, and this gives us T3 is equal to 1056.1 Kelvin. Now we are supposed to find out delta T, so we need T4, so we can find out T4 is equal to T3 upon Rp bracket raised to gamma minus 1 upon gamma, so it is 1056.1 divided by 4.533 bracket raised to 0.285, which turns out to be 686.49 Kelvin. So we can get T3 minus T4 is equal to 1056.1 minus 686.49, which is 369.6 Kelvin. So this is how we can find out the asked quantity, which is temperature drop across the turbine. Let us move on to the next example, which states that Brayton cycle has inlet conditions 100 kPa and 305 Kelvin and volume flow rate of 5 meter cube per second. Working pressure ratio is 10. Turbine inlet temperature is 1000 Kelvin. Find out efficiency, net work and back work ratio of the cycle. So let us see what are the things given to us in the example. Here new thing which is asked to us is back work ratio, and rest of the things are known to us, and we also know what is back work ratio. So we are told that P1 is equal to 100 kPa, T1 is equal to 305 Kelvin. We are told that volume flow rate at the inlet of the compressor is 5 meter cube per second. We are told that Rp is equal to 10 and T3 is equal to 1000 Kelvin. So now we are interested to find net work, for which mass flow rate is given, but it is given in meter cube per second as volume flow rate. So we can find out mass flow rate is equal to density at station 1 into volume flow rate at station 1. But we don't know density at station 1, but it can be found out from ideal gas equation, which is P is equal to rho RT. So rho is equal to P upon RT1 into volume flow rate. So P1 is 100 kPa upon R for the gas is 287 joule per kg Kelvin, and temperature is 305 Kelvin, and volume flow rate is 5, which gives us density as 1.1424 kg per meter cube as density, and then this density into 5 as mass flow rate. So we get mass flow rate as 5.712 kg per second. So the most required thing is Rp raised to gamma minus 1 upon gamma. So it is equal to 10 raised to 0.285, and it is 1.9275. Thus efficiency formula becomes very simple. 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So it is 1 minus 1 upon 1.9275, and efficiency becomes 48.11% or 0.4811. Now we are supposed to find out W net, so we should know all the temperatures at all the corners. So we can find out T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma. So T1 is 305 into 1.9275. So T2 is equal to 587.89 Kelvin. Then T3 is given to us, so we can find out T4, which is T3 divided by Rp raised to gamma minus 1 upon gamma. So it is 1000 divided by 1.9275. So it is 518.80 Kelvin. So for us, compressor work is m dot Cp into T2 minus T1. So m dot is 5.712 and Cp is 1.005 kilojoule per kg Kelvin. So it is 1.005 into 10 to the power 3 joule per kg Kelvin. So T2 is known to us as 587.89 minus T1 is 305. So compressor work is basically 1623.95 kilojoule per, basically it is kilowatt, kilojoule per second, so it is kilowatt. So turbine work is m dot Cp into T3 minus T4. So it is 5.712 into 1.005 into 10 to the power 3. This is in joule per kg Kelvin. So T3 is known to us as 1000 minus T4 is 518.80. So turbine works become 2762.36 kilowatt. So this gives us W net is equal to Wt minus Wc. So net work becomes 1138.40 kilowatt. Now we can find out RB, which is back work ratio, as compressor work divided by turbine work, and it is 1623.95 divided by 2762.36. So back work ratio is 58.78% or 0.5878. So this is how we would have solved the example on Brayton cycle. New thing in this example was we were given as volume flow rate in meter cube per second, so we were needing it to find out in kg per second. So next example, it states that air enters the compressor of a gas turbine at 0.1 megapascal pressure and 20 degrees Celsius. Air leaves the compressor at 1 megapascal pressure. Maximum cycle temperature is 1225 degrees Celsius. Find out compressor work, turbine work, efficiency of the gas turbine. So we are given implicitly everything, and then the thing includes the pressure ratio also. So 1, 2, 3, 4. So we are given that P1 is equal to 0.1 megapascal, 0.1 megapascal. So it is equal to 0.1 into 10 to the power of 6 pascal. So it is 10 to the power 5 pascal. So T1 is 20 degrees Celsius, and then it is 293 Kelvin, and we are told that P2 is equal to P3 is equal to 1 megapascal. So it is 10 to the power 6 pascal. Further, it is told to us that T3 is 1225 degrees Celsius, and that is 1498 Kelvin. So let us start evaluating. We first will find out RP, and RP is equal to P2 by P1. So it is 10 to the power 6 divided by 10 to the power 5. So it is 10. So our most important constant is RP raised to gamma minus 1 upon gamma. So it is 10 raised to 0.285, and it is 1.9275. Let us use this to find out all the temperatures at different corners. So T2 is equal to T1 into RP raised to gamma minus 1 upon gamma. So it is 293 into 1.9275. So T2 becomes 564.75 Kelvin. So we can find out compressor work, and it is Cp into T2 minus T1. So it is 1.005 into 10 to the power 3 joule per kg Kelvin. T2 is 564.75 minus 293. So compressor work is 273.12 kilojoule per kg. Let us find out T4. Since T4 is equal to T3 upon RP raised to gamma minus 1 upon gamma, T3 is 1498 divided by 1.9275. So we have T4 is equal to 777.17 Kelvin. This gives us Wt is equal to Cp into T3 minus T4. So Wt is 1.005 into 10 to the power 3 joule per kg Kelvin is equal to into 1498 minus 777.17. So turbine work for us is 724.43 kilojoule per kg. So this gives us net work as turbine work minus compressor work, and then that is 1724.43 minus 273.12. So this will be in kilojoule per kg. Further, we are asked to find out efficiency, and efficiency is 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So 1 minus 1 upon 1.9275, so it is 48.12%. So this is the formula for, this is the number for efficiency. So we were asked to find out compressor work, so we found out compressor work. We are asked to find out turbine work, so we found out turbine work. If we would have been asked to find out W net, then this would be W net, but we were not asked. So efficiency is this. So we found out all the necessary numbers which were required. Now having said this, we will move to the next example, and which states that a power plant based on Brayton cycle has pressure ratio 7, minimum and maximum temperature of the cycle are 25 degrees Celsius and 1000 degrees Celsius. Find the temperature at the exit of the compressor and turbine. Also find out back work ratio and efficiency of the cycle. Here we are explicitly asked to find out different temperatures. We would have used different formulas directly to find out the performance parameters, but we cannot use since we are asked intermediate numbers. So given things are Rp is equal to 7, T1 is equal to 25 degrees Celsius, which is 298 Kelvin, T3 is equal to 1000 degrees Celsius, which is 1273 Kelvin. Now we can go ahead. First we will evaluate most important constant Rp raised to gamma minus 1 upon gamma. So it is 7 raised to 0.285, it is 1.7412. Using this we can find out various temperatures. So T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma. So it is 298 into 1.7412, and it is 518.88 Kelvin. Further, T4 is equal to T3 divided by Rp raised to gamma minus 1 upon gamma. So it is 1273 divided by 1.7412, and it is 731.11 Kelvin. Thus we can find out efficiency, which is asked to us 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So efficiency is 1 minus 1 upon 7412. So this leads to efficiency which is 42.56%. 42.56%. So compressor work is Cp into T2 minus T1. So compressor work is 1.005 into 10 to the power 5 joule per kg Kelvin into 5.518.88 minus 298. So compressor work is 221.98 kilojoule per kg. Further, the turbine work is Cp into T3 minus T4. So turbine work is 1.005 into 10 to the power 5 joule per kg Kelvin. T3 is 1273 minus T4 is 731.11. So this gives us turbine work as 544.6 kilojoule per kg. So we can find out the asked quantity, which is back work ratio, which is WC divided by WT, and it turns out to be 40.76%. So we will move on to the last example. Here we are said that there is air which enters the compressor at 100 kPa and 25 degrees Celsius with volume flow rate as 8 meter cube per second. Working pressure ratio is 12. Temperature at the inlet of the turbine is 1100 degrees Celsius. Find out efficiency, net work and back work ratio. Again, similar thing, we are given that there is volume flow rate. So using the volume flow rate, we have to find out mass flow rate. Once the mass flow rate is known, we can find out net work in kilowatt. So given things are Rp as 12, P1 as 100 kPa, T1 as 25 degrees Celsius, which is 298 Kelvin. Volume flow rate is 8 meter cube per second, and T3 is equal to 1100 degrees Celsius. So it is equal to 1373 Kelvin. Now again we have to find out mass flow rate. So mass flow rate in general we can find out, since we are given volume flow rate at station 1, so we have to multiply by density at station 1 only. So density at station 1 into volume flow rate at station 1 gives us mass flow rate. So density is P1 upon RT1 into volume flow rate, and this gives us density as 1.169 into volume flow rate is given as 8. So this gives us 9.353 kg per second. Now having said this, we will again find out our basic requirement, Rp raised to gamma minus 1 upon gamma, which is 12 raised to 0.285, and it is 2.03. So let us first find out T2 is equal to T1 into Rp raised to gamma minus 1 upon gamma. It is so 298 into 2.03, and then that is going to give us 605.3 Kelvin. Similarly, we will find out T4, which is T3 divided by Rp raised to gamma minus 1 upon gamma. T3 is 1373 divided by 2.03 equal to 676.35 Kelvin. So we can find out compressor work in watt now, kilowatt, as m dot Cp into T2 minus T1. So compressor work is 9.353 into 1.005 into 10 to the power 5 joule per kg Kelvin. T2 is 605.3 and T1 is 298. So this gives us compressor work as 2886 kilowatt. Further, we can go ahead and calculate turbine work as m dot Cp into T3 minus T4. So turbine work is 9.353 1.005 into 10 to the power 3. T3 is 1373 and T4 is 676.35. So this gives us turbine work as 6548.35 kilowatt. So the asked thing is net work, which is Wt minus Wc, and it turns out to be 3662.34 kilowatt. Further, we are also asked to calculate back work ratio, which is compressor work divided by turbine work. So it is 44.07%. So we are asked to find out efficiency, and efficiency can also be found out as 1 minus 1 upon Rp raised to gamma minus 1 upon gamma. So 1 minus 1 upon 2.03, so it is 50.73%. So we are asked about efficiency, we have calculated. We were asked about back work ratio, we calculated. We were asked about net work, we also have calculated. So this is the way we can solve the examples which are related with the Brayton cycle, which is ideal, where everywhere we are considered all the components like turbine and compressor with 100% efficiency. We have considered CPCV or gamma as constant. So these things tell us that we worked with a standard Brayton cycle, which is ideal. Thank you.